Hello, my dear students. Welcome to my class Epatra Physics. In this lesson, we will learn about the conservative and non-conservative forces, potential energy, and power. First of all, conservative forces. A force is said to be conservative if work done by or against the force in moving a body depends only on the initial and final positions of the body and not on the nature of path followed between the initial and final positions. That means here not the force, the work done by the force or work done against the force is independent of the path followed. We are not saying that force is independent of path followed. Work done by the force or against any force, if it is independent of the path followed, net work done if that only depends upon the initial position and final positions, then that type of forces are known as the conservative forces. Example, gravitational force, electrostatic force, etc. These are the conservative in nature. To understand it, let us suppose a particle goes from point A to point B along the path 1. It is the path 1. And when a conservative force F acts on the particle, then the work done on the particle in the same along the path, path 2. And that means if the force involved here, that is conservative in nature, by the force or against the force, then work done to goes from point A to point B in path 1 or in path 2. In both cases, the work done will be the same. That means WAB along path 1 equal to WAB along path 2. In this case, when these two are equal, then we can say the force involved here, it is conservative in nature. Secondly, let us suppose a particle moves from A to B along path 1 and then B to A along path 2. That means it returns back to the same point by another path, but the initial point and the final point, that is the A point, were done by the conservative force along path 1 from A to B is equal to the negative of the work done from B to A along the reverse path 2. Therefore, WAB along path 1, which is equal to minus WB2A along path 2. And if the force is conservative in nature, and from this we can write WAB along path 1 plus WB2A along path 2 equal to 0. That means work done over a closed path, that is equal to 0. That means in a conservative force field, or when the force involved and during this process, during the work that is conservative in nature, and the initial point and final point same, that means the path followed, it is a closed path. The total or net work done in a closed path, that will be always 0 if the process conservative in nature. And another way we can write in this way, integration f dot ds over any closed path, this circular symbol, it represents the path, it is a closed loop or closed path. That means initial point and starting final point, that is also the same starting point. At that time, the total work done and equal to 0, and we can write in this way with the help of this symbol, the circle symbol gives or represents the work done in a closed path. Hence, a force is conservative if the work done by a force in moving particle around any closed path is 0. That means alternatively we can say the work done in a closed path is 0, or from A point to B point, the work done, if it is independent of the path followed, then this type of forces are known as the conservative in nature. Now, some basic properties of conservative forces. Number one, work done by or against a conservative force in moving a body from one position to other depends only the initial positions and the final position of the body, and this point is nothing but the definition of the conservative force, or what is the conservative force. Number two, work done by or against a conservative force does not depends upon the nature of the path followed by the body in going from initial position to final positions. That means nature of the path may be different type of nature. There may be slope, or in another way nature of path may be different, but total amount of work done to process from a same initial point to the same final point remains unchanged. Number three, work done or against a conservative force in moving a body through any round trip, that is closed path where final positions coincides with the initial positions of the body is always zero. That is also already we have discussed it, and these are the different points regarding to the conservative forces. Now, example of the conservative force, the gravitational force, it is a conservative force. We can easily show it that gravitational force, it is a conservative in nature. And to prove the gravitational force, it is a conservative force. Let us calculate the amount of work done against the gravitational force in moving the body of mass m through the same height h over the different path from A to B. That means, let us suppose initially the object will be on this zero energy levels, and here placed here, and it has to shift against the gravity from point A to point B. But in the first case, we are directly shifting it from a point A to point B, and in this case, obviously, work done that will be mg into ab, that is mgh. Directly we can find out the what is the work done against that gravitational force, and that is mgh. Let us suppose the object is not shifted directly from point A to B. It follows this like of path from A to C, then C to D, then D to E, and then E to F, F to G, and again G to B. That means in several steps it is shifted from point A to point B. Now we have to calculate what is the total amount of work done, because path length is now more than the first cases. In the first case, it is directly shifted from point A to B, but in the second case, we are considering there are different paths followed by the object during the shifting from same point A to point B. And now we can also here show that the total amount of work done is nothing but equal to the work done in the first cases, that is mgh. Now let us suppose the body is raised through the same height h, but now along the path A, C, D, E. In this way, F, G, B, as shown in the figure diagram B. Here, during the horizontal path AC, DE, and FG, force of gravity is perpendicular to the displacement, so work done is zero. The work done is done only along the vertical path CD, EF, and GB. In this figure diagram, we can easily say in the first displacement, that is from A point to C point, and that is horizontal displacement, and that is the perpendicular to the mg, and therefore work done to shift point A to C against the gravity 0. And here also DE, it is another horizontal path, and FG, it is another horizontal path. Therefore, the to shift A to C, D to E, F to G, in these three paths, there is no work done against the gravity, and only the vertical shifting taken place, that is C to D, that height is the H1, and E to F, that is height is the H2, and G to B, that is height is the H3. In these three steps, work will be done against the gravity. Therefore, we can now write work done from A to C, that is horizontal displacement, that is 0, and we say it is the W1. Work done to raise the body from C to D. Here there is a height shifting, that is the H1, and therefore the work done from C to D, that is the MGH1, and we are saying that it is the, let us suppose, W2. Again, work done in the horizontal path at D to E, that is the 0, let us suppose W3. Work done in to raise the from E to F, that is MGH2, that is W4. Work done from EF to G, that is 0, that is the W5. Work done to raise from G to B, that is MGH3, that is W6. That means there are 6 type of displacement. There are 3 horizontal displacement and 3 vertical displacement. Naturally, in the horizontal displacement, there is no work done, and only in the vertical displacement work done, C to D, E to F, and G to B. And these are the different, therefore, total net amount of work done to shift the body to a height h from point A to and final point B, and that is in the path A, C, D, E, F, G, B. So that is W is equal to W1 plus W2 plus W3 plus W4 plus W5 plus W6. Physically 0 plus MGH1 plus 0 plus MGH2 plus 0 plus MGH3. And if we take the common MG, then H1 plus H2 plus H3, and that is nothing but the total height H. Therefore, H is equal to H1 plus H2 plus H3. Therefore, total work done again, that is mgh. That's the work done in moving the body against the gravity is independent of the path followed, but depends on the initial and final positions of the body. Hence, gravitational force is conservative nature. That means we can easily say now, since the power done, that is mgh, when it is directly shifted from A to B, and when it is moved through the path A, C, D, E, F, G, B, in both cases the work done is the same against the gravity is the same, and that is equal to mgh. Therefore we can easily say gravitational force, it is a conservative force, and that is a basic consideration or basic criteria to say a force is a conservative in nature. Now obviously when we are saying there is a conservative force, there also will be non-conservative forces. Just definition is just refers to it. A force is said to be non-conservative if work done by or against the force in moving a body from one position to another depends on the path followed between these two positions. Here, it is not the independent of the path followed. That means when the object shifted from one point to another point under the action or effect of the non-conservative force, then work done will be different when it moves from the same point to other same point, but in the different paths. Example, force of friction and viscosity are non-conservative forces. Work done by or against a non-conservative force appears in some other forms of energy like heat, sound, light energy. Work done by a non-conservative force on the body around a closed path is not equal to zero. That means here closed line integral of f dot ds, that means f dot ds over any closed path not equal to zero. And it is another important point, but in case of conservative forces, when any work done against that conservative force, that amount of work will be stored in the form of potential energy. And we are now basically will study the potential energy, and at that time it will be said that when the force is conservative in nature, work done against that force, that work done is not converted into other form of energy, it will be stored in the form of potential energy. But in case of non-conservative force like frictional force, any work done against the frictional force, that somehow partially or fully convert into the heat energy. Now our next topic is the today's lesson, that is the potential energy. Potential energy, it is general term. There are different types of potential energy. The energy possessed by a body by virtue of its position or configuration is called potential energy. That means in our previous classes we have learned about the kinetic energy. The virtue of its motion, energy possessed by any object is the kinetic energy. But here the virtue of position or configuration, and it is you have to say position in a conservative force field, or when it is deformed or there is a change in the configurations, and at that time a conservative force is involved, then it possesses some energy, and that is the potential energy. Or simply you can say energy possessed by a body by virtue of position and configuration is called potential energy. Potential energy is also called as mutual energy or energy of configurations. It is measured by the amount of work that a body or system can do in going from the present position or configuration to some standard positions or zero configurations. That positions is called zero positions or zero configurations. That means the initial positions and or a particular positions or a particular configuration that is taken at the zero configuration or zero positions, and from that zero positions or zero configurations, the when it is shifted to other positions or give another configurations, and for that what is the amount of work done, that amount of work is stored in the form of a potential energy. There are different types of potential energy. Potential energy of many types. And there are three basically common types of potential energies. Number one, gravitational potential energy. Obviously, this energy is associated with the state of separation of two bodies. These bodies attract each other through gravitational force. That means when any object is placed in a gravitational force field or subjected to gravitational force, at that time due to the position in that gravitational force field, the object possesses some energy, and that energy, gravitational potential energy. Another very common potential energy, that is the elastic potential energy. This energy is associated with the state of compression or extension of an elastic object. That means when any object is deformed, that means the configuration from the zero configuration is changed. At that time it possesses some energy, or is some energy is stored in the different conditions when any spring, example, compressed or extension taken place at that time. Due to this compression or extension, or that means change of the configuration, it possesses some energy, and that is elastic potential energy. Another very important potential energy, that is electrostatic potential energy, that is somehow commonly known as the electrical energy. This energy is due to the interaction between the two electric charges. And here, first of all, we will discuss about the gravitational potential energy. It is the energy possessed by a body by virtue of its position in a gravitational field of Earth. And when we consider, there is a common sense of the potential energy. When we consider any type of potential energy, and there is must be a conservative force behind it. And that means when any object is subjected to some force field or conservative force, then it possesses energy. Obviously, when it is subjected to some gravitational force, then it possesses potential energy, that is gravitational potential energy. Let us body of mass m lie on the surface of the earth, g, small g, with the acceleration due to gravity at that place. The body is being pulled with a force equal to weight mg acting vertically downwards. That means there is a shifting of the object against the gravitational force. Let us, the body of mass m is to be raised to the height h above the surface of earth. The force required to lift the body must be equal to gravitational force. Therefore, applied force, that is equal to gravitational force, that is equal to mg. The work done by the applied force against the gravitational force, that will be F dot h. That means the displacement taken place, h is the displacement here along the direction of the applied force. Therefore, F into h cos of 0 degree, where F is the applied force, h is the displacement, and 0 angle between the applied force and the h. Since applied force parallel to the displacement h, therefore we can write it is Fh cos of 0 degree. That means what is the work done? F into h, that is mg into h. Therefore, net work done by the gravitational force on the body in raising through height h, that will be F gravitational force dot h, that is Fh cos of 180 degree, that is minus F into h, that is minus mgh. Now it is so in this process, the work done by the gravitational force, that is minus mgh, when is the object is lifted through a height h from the standard 0 level, and work done by the gravitational force in the same event, same process, that is minus mgh. And that is this work gets stored as a potential energy. Then what is the potential energy? The gravitational potential energy of a body as the function of height h is denoted by the ug, capital U. Internally it is denoted by the capital U, and it is negative of work done by the gravitational force in raising the body of the height. That is gravitational force, that is the P into E, that is potential energy, is equal to mgh. And here we are saying in this way, the work done, negative work done by the gravitational force, negative value of that work done, and minus into minus, that will be the plus, and the positive value of the work done by the applied force, which is equal to negative value of the work done by the gravitational force. Applied force, there may be different agencies, but gravitational force, that is always mg, that is fixed. Therefore, when we say about the change in the potential energy, the gravitational potential energy, at that time, for the reference, we are taking the gravitational force. Therefore, work done by the gravitational force, work done by the gravitational force, the negative value of the work done by the gravitational force, that is change in the potential energy. We can understand it is in another way. Let us suppose object is moving downwards, it is freely falling object. Therefore, work done by the gravity is the plus mg, because the mg and the displacement both are taken place downward direction, same directions. So in such a case, the work done by the gravitational force is the plus mgh, and therefore the what is the potential energy change? There is the minus of plus mg, there is minus. Therefore, we can say when the work done by the conservative force is negative work done, the potential energy increases, and when the work done by the conservative force is positive one, then potential energy will be negative. That means decreases. Potential energy relation to the conservative force, there is a relationship between the potential energy and conservative force. And obviously, when we say potential energy, there must be related to a conservative force. Any single object cannot possess any energy until when it is not placed to any conservative force field. Therefore, the potential energy and conservative force field, these two are related to very close to each other. The potential energy of a body is the energy associated or possessed by body by virtue of its configuration in which conservative force acts. Let us consider that a conservative force Fx, that is a function of x variable maybe, and does a work W on a particle within system. Change in the potential energy delta U of the system is equal to the negative of work done performed by the conservative force. Already we have stated it. This statement is very, very important. That negative of the work done performed by a conservative force, that is equal to delta U, change in the potential energy. If the work done by the conservative force is negative, negative into negative, the energy will be d will be positive, and when the work done by the conservative force is positive, then energy change will be the negative. Therefore, we can write delta U, that is change the potential energy, that is minus W, where W is the work done by the conservative force. But W is equal to, in a, we know that is xi to f, that is fx dx. Therefore, we can write mathematically, it is one mathematical statement, delta U, that is minus xi to initial x to final f x fx dx. If we differentiate both sides, then we get du by dx is equal to minus f of x. Differentiation, it is a reverse process of the integration. Therefore, to find out the f, we can differentiate both sides, and it is the relationship between this fx, that is conservative force, and that is negative potential energy gradient. It is one very important relationship. That means at any place when any object is subject to some conservative force, therefore it must possess some energy. And what is the relationship between the energy and the potential energy and the force? The force is nothing but negative potential gradient with of the potential energy. Here negative sign indicates if we proceed in the direction of the force, the potential energy decreases. Here negative sign indicates. And hence potential energy U may be defined as the function whose negative gradient gives the force. Conversely, we may define the conservative force as a force which is equal to negative gradient of the potential energy U. Therefore, the work done by a conservative force on a body is independent of path and depends only on the end points. That is W is equal to, we can write it is xi to xf fx dx, that is the final kinetic energy minus final initial energy, and which is the initial potential energy minus final potential energy. That means in lieu of the kinetic energy converted into potential energy. Also from this we can say potential converted into kinetic energy when the force involved in the event that is conservative in nature. If an object moving around any closed path returns to its initial position, that work done by the conservative force is zero. It is repeatedly again, that is the work done over a closed path, that is closed integral line, integral of the fx dx is equal to zero. Now our last topic is today's lesson, that is the power. Power, it is also a scalar quantity. Obviously, power is generally defined as the work done by time taken, the rate at which the work is done, or it is rate of doing work. This power equal to work done divided by time taken. The power of a body measures how fast it can do the work. That means maybe one object or one person possesses some more amount of energy, but that is total amount of energy is not the measurement of the power. Power means how fastly it can do some work, how rapidly any machine, any engine, any person do some work. I mean, what rate of time rate of work done when more, that person, that machine, that engine will be said it is more powerful. When a body takes lesser time to do a particular amount of work, its power is said to be greater, and vice versa. That means in the less time, if anyone do more work, that person or that machine is more powerful, and we can measure it with the help of this dw by dt. If you say about the average power, that means total amount of work done in delta w divided by in time interval delta t. The delta w by delta t, that is average power. the power at any agent may not be constant. That means when we are taking the average power, that means we are considering the power somehow constant. But in practical situations, the power of any agent may not be constant during that time interval or during a larger time. So we define the instantaneous power, and therefore instantaneous power actually real power at any moment, and that is more important. The instantaneous power is defined as the limiting value of average power when the time interval approaches zero. In all cases, when we find out the instantaneous, then we are considering the limiting value of the time interval, that is delta t tends to zero. It means delta t is very, very small, not equal to zero, and it is nearer to zero means it is very, very small. And if we take this time interval is very, very small, then we get delta W by delta T, limit delta T tends to zero, we get P is equal to dW dt, and it is known as the instantaneous power. That means at any instance, what is the instantaneous power? That is dW by dt. And we know from our work relations, W is equal to F dot ds. So if we write in this way, W is equal to F dot ds, differentiating that is W, and considering the F is constant. If F is constant, then we can write that is F dot ds vector dt, and that is nothing but the V. It is another formula for the power, that is F dot V. It is also very well-known formula. Power, it is also scalar quantity. Therefore, we are taking here dot product. Actually, it is coming from the work. Work is also result of the dot product of the force and displacement. And here, power is the dot product of the force and velocity. Thus, power of an agent at any instant is equal to the dot product of its force and velocity vector at that instant. The P is equal to F dot V vector, that is Pf V cos of theta, where theta is the angle between the force and the velocity at that moment. And if theta is 0 degree, that means F and V in the same directions. Naturally, at that time, cos of 0 is the one, that is the maximum value of cos theta. Therefore, power will be maximum, and that maximum power will be F into V. That means when the force and the velocity both are acting along the same directions, the power will be maximum, and that maximum power directly we obtain by multiplying F and V. It is a scalar quantity, and we can another basic term related to the power, that is the dimensional formula. The dimensional formula of the power is the W by T. W, that is the work, that is ml2 T minus 2 divided by T, or which is equal to ml2 T minus 3. That is the dimensional formula for the power. And SI unit, that is the unit of work divided by unit of time. And in SI system, the unit of power is the watt, and obviously 1 watt is the 1 joule per second. That means the power of an agent is said to be 1 watt if 1 joule of work is done by it in 1 second. And that means per second, if the work done is the 1 joule, the power is the 1 watt. If it is 5 joule per second, that is the 5 watt, etc. In CGS system, the unit power visually arc per second, arc is the unit of work, and second is the unit of time. And this is the CGS system. But bigger unit of power, that is the kilowatt, megawatt, etc. When we think about the larger unit, that is a kilowatt, megawatt, and 1 kilo means 1000. Therefore, obviously 1 kilowatt means 10 to the 3 watt, and mega means 10 to the 6. Therefore, 1 megawatt equal to 10 to the 6 watt. Practical unit of power, that is a horsepower. It is British unit of, and 1 horsepower actually that is equal to 550 feet pound per second, and that is average power of an horse. And when we convert it into SI system, it is approximately equal to 746 watt. But it is not the in CGS or SI system, it is in British system. And on an average, it is power of an horse, and that is in a SI system, which is approximately equal to 746 watt. It will be required in future. Now, power and energy. And we are defining here work done by time is the power, but equally we can say power is the energy by time. And when we saying about the power of any instrument which consumes some energy, which produce some energy like generator, electric motor, etc., and electric energy or other form of energy. And at that time, we are not only saying that work done by time taken, that is energy by time taken, and work done is equal to energy supplied or energy consumed, work done. Therefore, energy, actually, measurement of energy is taken by the work done. Therefore, we are saying the work done is equal to energy supplied or energy consumed. That means not only the work done per second, the energy supplied per second, energy consumed per second, supplied per second. That means for a power generator, which energy supplied per second, or any electrical appliance which consumed per second. These are also the power, and the unit is the same. Work done per unit time or energy per time. Energy equal to power into time. And now one unit, already we have discussed it, that I am repeating again, that the commercial unit of energy. The commercial unit of energy is kilowatt hour, or it is also known as the board of trade unit. And basically it is used in electrical energy in our home. And when we pay bill, electrical bill, then we have to pay per unit, and that unit is the BOT, and that is nothing but the 1 kilowatt hour. And 1 kilowatt hour is the electrical energy consumed by an appliance of 1000 watt in 1 hour, or 1 kilowatt, that is the 1 kilowatt in 1 hour, that is 1000 watt in 1 hour. And if we convert it into SI system, that is 1000 joule per second into 1 hour, means 300 3600 seconds. And from that we get 3.6 into 10^6 joule. It is equal to the 1 BOT, that is one commercial unit, this one. And it is the end of today's lesson, and we will meet in the next lesson later on. Now we end this today's class.